All right, so I would like to review this great book, the first book of Eichfelder in 2008, because it is essential for the subject of multi-objective optimization, the modern view. So the basic definition is the k-minimal points. What is a k-minimal points? There are some points that if you make intersection of, so this is y bar minus, this area is y bar minus k, intersection of that with t, it should be y bar. If it is y bar, then we say that y bar is a k-minimal points. We need these because we want to make a structure, we want to create a partial order so that to say which point is preferred to another point, is better than the other point. So when k is pointed, then this is the definition of k-minimal point. For example, you want to minimize y1 and y2 and also y2 minus 1. So you have three objective functions and you want to minimize them. In order to say which point is better than the other point, we need these three inequalities. And so from them, we can create our own cone. So this is the cone. But in general, you want in portfolio optimization, for example, it could be arbitrary, and you need to care about it is pointed. The origin is inside cone, and it is closed and convex. And so convex polyhedral cones are special cones because, first of all, you can define them by some matrix, for example, kx, which k is a matrix, and they are finitely generated. Unlike ice cream cone, which is, for example, here like this. This is, you need infinite number of rays to generate them. So the base is infinite. But polyhedral cones are finite. You just need a finite number of these bases, vectors or rays, in order to generate the whole space inside this cone. And this is an example of a cone which is not finitely generated. You need infinite number of rays to generate them. And you have seen that I use one of the tricks to formulate Markowitz problem using this one. And so convex polyhedral cones are finitely generated. So we just need finite number of vectors to generate them. And so we need the concept of cone in order to find the efficient point of your frontier, to find all the points of the efficient frontier. And I will show you that in Pascoletti Serafini, we only need A and R and K. We keep K constant in this book, but it can be varied as well in this article and in the second book of Eichfelder. But in this book, we only assume that A and R, we vary these two parameters only. Even most of the time, if we keep R fixed and we vary A in a hyperplane, we vary A to find all the efficient points of. And for example, if your objective space is three-dimensional, you can see that you can find the equivalent problem by going even to higher dimensions. So here we have four objectives, although the original space is three-dimensional. But because in this problem, our cone has become EP minimal. You are using are 4 positive only. So your cone is very simple, and that's the gain you get. So we want to solve this multi-objective optimization problem, but you need we want to approximate it with Scaletti. This is Scaletti Serafini, Pascoletti Serafini. So we need to minimize this, and A plus C, this one should be inside our cone. So the relationship is obvious in this theorem, especially this one, that is X bar is a weakly K-minimal solution of multi-objective. Then 0 and X bar, I mean putting T is equal to 0 and X is equal to X bar, then this is a minimal solution of SP problem, serafini-Pascoletti. And so you see, we have connected the weakly minimal solution, just a weakly minimal solution of MOP is enough. We can connect it to a minimal solution of Pascoletti Serafini. And so you see that this problem, you can define it like this. So for any A and R, you have a completely different optimization problem. And as I said, the point is K minimal if this condition satisfies. So we are trying to go in some directions. Directions are when A is your reference point and T is the amount of points that you go in this direction. And we can rewrite this problem, I mean SP, in another form as well. So both of them are equivalent. This one is equivalent to this one. And of course, as I said, some people use variable cones. And so the problem of parameter set restriction for 2D, we can show you that that even knowing that 2 points, A1 and A2, then all the convex combination of any of these 2 points, which is all of these points, is enough to search in this area, and we don't need to search in all of the space. And you need to know that you need the reference point is here, and the amount that you need to calculate this T bar is so if you put A and T bar, you are on this hyperplane. For example, this is one A, this is another way, and all of them you go in direction R. You go in direction R to some efficient frontier. So these are the points on the efficient frontier. You want to minimize these such that when you go in this direction, it intersects them and becomes the minimal T that satisfies that K minimality condition. And the proof is really easy. And if you just put T bar and A as is said in the theorem, you can see that you can use the properties of the cone, and by contradiction you can prove this theorem. And for the bi-criteria case, it's very easy. I mean, geometrically, you can say that if you are on this hyperplane, that your hyperplane in 2D are just some vectors, you know. But in 3-dimensional is a space, in 4-dimensional you call it hyperplane, and so on. So if x1 is a solution of L1 transpose f of x, and x2 is a solution of L2 transpose, so our polyhedral cone is derived by just 2 basis vectors, 2 rays, L1 and L2. And the matrix that I said K is 2 by 2. And we have a lemma that shows that You just need to point to care about A bar and T bar. If you define A bar and T bar like this, then T bar and X bar is a minimal solution. And the proof is very simple. So we are projecting the space on the objective space. We are projecting it on the projecting to a hyperplane. This is the hyperplane that in 2D is just a line, and it is enough to initialize A. If we just set A on this line, then if you go, you can find some minimal points on the efficient frontier. And for 2D, as I said, it is you can also find the bounds on that, which we cannot do obviously in 3D, because in 3D it's such a it's something like this. How can you find some bounds very easily? So you bound it by a cubic which is inside a hyperplane, and then try to do whatever we have done in 2D dimensionals for high dimensions as well. So it's just a convex set, your hyperplane convex combination of those points. You get all the space that you need for A. So you just put A on this hyperplane. And as I said, for general case, we try to approximate it by some hyperplane. And this hyperplane has a basis vectors, V1, V2. These are vectors on that. And that from calculus, that, as a plane, a hyperplane can be formulated like this one. And so you need to know the lower, this is the S mean and S max, for example, in dimension 1. And dimension 2, the coordinate 2 is like this. Mean and S2 max is in dimension 2. So you are trying to bound it. And that's why these things are talking about. So these S mean and S max is all of them trying to define a cuboid. And so we are talking about modified Pascoletti Serafini for theoretical reasons, because it is easier to work with, especially the Lagrangian that I will talk about in the next 2 lectures. So here the inequality constraint is just equality because we are just touching the point 0 inside because it's K is a pointed coin, so 0 belongs to this point as well.